Hi, my name is Amanda Hegadorn, and today I'm going to walk you through using a National Instruments MyDAC to implement and test two finite state machines. We will use these ICs and configure our MyDAC to read on pins 4 to 7 and write on pins 0 to 3. The purpose of a finite state machine is to retain state information in a flip-flop and proceed to its next state based on the previous stored state and a user input. The first state machine we will build is given in the lab and has the following flowchart and truth table. Our goal is to implement the circuit and test it, filling in a state table and comparing it to the truth table here. To implement this state machine, we'll follow the logic in this diagram. Important things to remember are that the outputs of the decoder are inverted, which explains some of the logic here. First, we set up our breadboard, connecting power and ground from the MyDAC to all power and ground lines on the board. Next, we set up and test our decoder. There are 3 enable pins, 2 which will set high and 1 which will set low because we always want the decoder to be enabled. Then we can test the decoder by connecting 3 input pins, 0, 1, and 2 to A0, A1, and A2 and test the outputs, watching for active output to go low. Next, we'll set up the flip-flop by placing it on the breadboard, leaving space for logic gates in between. We supply power to the chip, and we also connect an unused output from the MyDAC to the clock input on both sides of the board. We connect the clear and preset pins to power in order to avoid using them. We also connect the output to pins 4 and 5 on the MyDAC so we can read the current state. Next, we connect the logic by taking output Y1 from the decoder through the NOT gate, the bottom IC, before attaching it to the input on the right side of the flip-flop, the green and white wires. You can also see the 2 white wires from outputs Y2 and Y4 that go through the NAND gate. Now we have our entire flip-flop wired and can test. We'll test as we fill in the state table, and you can see our results in the following clip. Here, any state with an input of 1 leads to state A. State A with an input of 0 leads to B, B with an input of 0 leads to C, and C stays at C. We know that our circuit is correct because our state table matches our truth table. Next, we'll design a state machine given only this table to begin. With the flowchart, we're able to populate a truth table by following the diagram given a state and an input. This allowed us to create 2 K-maps, one for the next state and one for the next state 0. These K-maps helped us isolate which decoder outputs result in a state change. It could be boiled down to the statements in this chart. These statements were used to create a wiring diagram with pin numbers shown here. When implementing this, we needed 3 NAND gates and a NOT gate. Note that when implementing a 3-input NAND gate, it's the same as an inverted NAND gate fed into a second NAND gate. To implement this circuit, remove wires from the NAND and NOT gates from the previous setup and replace them according to the diagram. We can test this again by using the MyDAC inputs where pin 0 is X, the input, and pin 3 is the clock signal that triggers the state change. We know that this is correct because the state changes here match our truth table and initial diagram. We were also able to populate this chart. Thank you.